This is section 9.9, representation of functions by power series. All right, so we had seen a function e to the x that we represented by an infinite series, a power series. And so we're going to continue thinking about that kind of thing here for just a bit and talk about another function. Let's start with this one. F of x equals 1 over 1 minus x. As an aside, you probably will remember that a geometric series that converges a convergent geometric series has the property that it converges because the absolute value of r is less than 1 and not 0, so greater than 0, and diverges when the absolute value of r is greater than or equal to 1. And if it converges to the sum a, the first term, over 1 minus r. Now, I'd like for you to look at the function I wrote over there to the left and think about how that function, the way it's written, looks a whole lot like our formula for s, constant over 1 minus a function of x. So if we consider your generic geometric series, that's our first term times r to the nth, starting with n equals 0. As we said, that converges to a over 1 minus r when the absolute value of r is less than 1. Otherwise, it diverges, does not converge to a sum. So if we think of our function 1 over 1 minus x, where I let a equal 1 and r equal x, we could write a power series representation for this by thinking of it as a geometric one where a is 1 and r is x, which of course 1 times anything is just that thing. So this would simplify to be sigma from n equals 0 to infinity of x to the nth. And you'll notice that I don't have like x minus 2 or something there raised to the nth, so this one is centered at 0, this particular one, which of course means c is 0. And if we were to expand that, x to the 0 is 1 plus x to the first plus x squared plus x cubed plus dot 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 plus x to the nth plus dot dot dot. And that will converge as long as what we have called r. So let me go over here and write down what we did. We let a equal 1 and we let r equal x. And so the function f of x equals 1 over 1 minus x converges to the power series written to the right the sigma notation version being sigma of x to the nth, and the expanded version being 1 plus x squared, etc. As long as r, which in this problem is x, its absolute value is less than 1. And if we took out the absolute value, that would mean that x is between -1 and 1. And recall up here where we said that the geometric series, which is how we're treating this particular function, the geometric series does not converge when r is equal to 1, nor does it converge when r is equal to -1. So, in this particular instance, we do not have to check the endpoints like we did before with the ratio test or a root test, because if you're using a geometric series idea, like we did here, when it looked like some number over 1 minus some function of x, it will only converge when the absolute value of r is less than 1. So we never ever have to check the endpoints when we treat it as a geometric series. So that's gone. Don't worry about it. We do not have to check that out when it's geometric. Okay, so this is a good kind because you don't have to check those endpoints. Now, that's a very narrow interval of values for x. F of x equals 1 over 1 minus x only if you're using x's between -1 and 1. Okay, so if we think about what the graph of that function looks like, oops, I'll pretend like that's a straight horizontal line there. It's not, but pretend with me. So if that's 1, we have a vertical asymptote for that function at x equals 1. Put a few more marks on the axes here. And the graph looks like this. This is the entire function. Okay. Looks like this. And the function f of x converges to that series only for that limited domain. So it's actually only valid from -1 with an open circle there to 1, and I don't need an open circle there because there's a vertical asymptote instead. And so that's all we're getting is that part of that function. We're not getting anything to the right of x equals 1. We're not getting anything to the left of -1. So, or -1 even. So that's kind of a narrow band. And to get a different interval, we're going to have to develop a different series. So let's go through that process. Let's say we wanted it to be centered. Instead of at 0, put the center at -1 instead. So we're going to take the expression of our function 1 over 1 minus x and rewrite it so that it's centered at -1 this time. Now if it's centered at -1, we're expecting to see x minus c. So x minus -1 is the same thing as x plus 1. We need to see that in our re-expression of 1 over 1 minus x. So let's do this. Let's take the original expression and change it so that its value is the same, but it looks different. So what I'm going to do here is I'm going to, in the denominator, I'm going to add 0 in the form of -1 plus 1. Hopefully you'll agree that I haven't changed the value because all I've done is add a form of 0. Then, if I insert a parenthesis in front of the x, anything that goes in there will have to change sign, so that minus x will become positive x, and that negative 1 will become plus 1. And that's what I want inside the parentheses, so anything that's left is going to stay outside, and that becomes plus 1. Still is plus 1 because it did not go into the parentheses. Then simplifying by collecting like terms, you'll get 2 minus x plus 1. So far I've done a good job in rewriting that almost in the form I need. It's definitely such that I know the center is at x plus 1. Now, keeping in mind all the time, you need to keep this in your focus. Whoops. Let me erase that. We need a constant over 1 minus r. So a is a number, a constant, and r ends up being a function of x. Like in this problem, we wanted x plus 1. That's what we're hoping for, to be able to use this geometric series to be able to rewrite this one as a power series. So you might notice really quickly that this right here has to be positive 1. And so a lot of times after you've gotten your center binomial correct, so centered at negative 1, the binomial becomes x minus negative 1, so x plus 1. Once you've dealt with that issue, the next big issue is you've got to multiply this one by a form of 1 so that that 2 becomes a 1. To make that happen, I would multiply by 1/2 to change 2 into 1. And of course, I have to multiply by 1/2 over 1/2 to make that happen. And distributing, that becomes 1 minus x plus 1 over 2. So at this point, we now have this written in the form of a over 1 minus r. And what we'll need to do is identify what part is a, which part is r, and then we can talk about what the series is and what it converges to. So a is the number in the numerator, so it's 1/2. R is the function of x subtracted from 1, so that's x plus 1 divided by 2. And the series, this series, which is now centered at a different place, not 0, for 1 over 1 minus x, will be sigma from n equals 0 to infinity of a, which is 1/2, times r, which is x plus 1, over 2 to the nth. And of course, if we expanded that out, there would be a 1/2 we could pull out in front, and we would have, if we put in 0 for n, we'd get x plus 1 over 2 to the 0 is 1, plus, now put 1 in for n, and we get x plus 1 over 2 to the first. And put 2 in, and we'll get x plus 1 squared over 2 squared, which is 4. Then put 3 in, and we'll get x plus 1 cubed over 2 cubed, which is 8. etc. And that converges when R, when you take the absolute value of R, I should have said, the absolute value of R is less than 1. So that becomes the absolute value of x plus 1 over the absolute value of 2, which is 2. So the absolute value of x plus 1 multiplying both sides by 2 makes that less than 2, which means that x plus 1 is between negative 2 and 2. Subtracting 1 from everywhere, you get negative 3 is less than x is less than 1. So our interval of convergence is negative 3 to 1. So whereas before we went from negative 1 to 1, right here, that was the interval of convergence up here. By having the center at negative 1, the interval of convergence is now from negative 3 to 1, a bigger set of values. Okay. So, oh, and should we check the endpoints? No. If we treat it like a geometric series and make the absolute value of R less than 1, we do not need to check the endpoints because geometric series never converges when R is 1 or negative 1. All right, so let's do another problem. Let's say, for example, f of x is equal to 4 over x plus 2. Now, if that or any function is writable in the form a over 1 minus r, then we can treat it geometrically and come up with a series and its interval of convergence actually quite easily. The biggest trick is getting it in that form. So one of the things I'm concerned about is that this is addition in the denominator, not subtraction. Of course, the good news is the definition of subtraction says that it's the same thing as addition of the opposite. So I can change this into subtraction of the opposite. That's the same thing as 2 plus x, and now it's subtraction. Now the next issue, because otherwise it's looking pretty good, is that 2 has to become a 1. So multiplying by this form of 1, 1/2 over 1/2, we get 2 over 1 minus the opposite of x over 2. Okay, so equating that to a over 1 minus r means that we're going to let a equal 2, and we're going to let r equal the opposite of x over 2. So the series for this function, 4 over x plus 2, would be treated geometrically, starting at n equals 0 and going to infinity. A, which is 2, times r negative x over 2 to the nth is what that series would be. Okay, and if you chose to expand that, 2 is something we could pull out front. Now putting 0 in, negative x over 2 to the 0 is 1. Plus, when I put 1 in, I'll get negative x over 2 to the first, which is negative x over 2. So plus a negative is subtraction. Plus, then put in 2. So negative x over 2 squared is x squared over 4, positive. Put in 3. Negative number cubed is negative, so minus. Putting in 3, that'll be x cubed. over 8, etc. Okay. Now, we'll be able to write that series for 4 over x plus 2 for the x's for which it converges. And this converges when the absolute value of our r is less than 1. Well, the absolute value of the -1 part of that is 1 times the absolute value of x divided by the absolute value of 2, which is 2. Then, multiplying both sides by 2, you get absolute value of x is less than 2. So, without the absolute value, that inequality is -2, less than x, less than 2. And so that means that the interval of convergence is -2 to 2. All right, so if you look at the next slide, operations with power series. If you have two different functions, f of x, which will use the coefficient a sub n, and g of x, which uses the coefficient b sub n, but otherwise they're both power series. Then if you have f of kx, so like instead of f of x, you have f of 2x or f of 7x or something, then that becomes something that you can just deal with like this. So take the sigma declaration for f of x. Oops, yeah. And where the x is, replace it with kx. Just substitute it in. And then, you know, a power on a product, you know that property is you distribute the power to each factor. So this will be a sub n times k to the nth times x to the nth. Okay, which is the way the property shows. Well, so I'm basically giving you the version of substitution. Now, so as not to confuse n's, they're going to call this a power of x, and this power of x is capital N, not to be confused with the lowercase n we're already using. So we'll go into the series expression for f of x, take out the x, and in its place put x to the capital N, which is raised to the little n power. Then we'll use the property of powers on powers, which has us multiply the exponents. And so this will become x to the n times big N. Okay, which is what you see in the operations with power series box. Then the sum or difference of two series will, let me write that down. Is, by substitution, a sub n x to the nth plus, and then g of x is a similar looking thing, but the coefficient is ruled by the letter b, so b sub n x to the nth. And you can combine those two sigmas that are added or subtracted into one sigma. That'll be a sub n x to the nth plus or minus b sub n x to the nth. And for those two terms, there's a common factor of x to the nth, which we can take out by factoring, kind of the reverse of distribution, and get that answer. Okay. So, example 2. Find a power series for this function, f of x equals 3x minus 1 over x squared minus 1. Well, at first glance, you should be a little bit dismayed because there's no way, the way it is right now, that that numerator is a constant. Remember, a over 1 minus r is how we have to treat this, and so that can't work. But luckily, we have something from earlier that we did that we can use to make this so that it works to our advantage. So first of all, maybe you'll know what I'm talking about if I write the factored form of the denominator. Does that help you? Do you know what I'm talking about? Well, this can be rewritten using partial fractions, where there's going to be some number over one of my factors, x plus 1, plus b, an unknown constant, over my other factor. So yes, you still need to remember how to do partial fractions. So as a review of that, we multiply both sides by x plus 1 and x minus 1, getting 3x minus 1 on the left side, and a times x minus 1 from the first fraction, plus b times x plus 1. And so if we let x equal positive 1, 3 times 1 minus 1 is 2. 1 minus 1 is 0, so the a part, it becomes 0. 1 plus 1 is 2, so that becomes 2 times b, which means we can solve for b by division, and it's 1. Then if we let x equal negative 1, negative 1 times 3 is negative 3 minus 1 is negative 4. Negative 1 minus 1 is negative 2, so that's negative 2a, plus negative 1 plus 1 is 0, that term becomes 0. Dividing by negative 2, we get that a is 2. And so, going back to our function, that means that f of x can be rewritten as a, which is 2, over x plus 1, plus b, which is 1, over x minus 1. Okay. So, let's see if we've done anything prior to this that will help us with this one. 1 over 1 minus x. Yeah. That looks kind of familiar. Well, I'm going to go ahead and do these from scratch, even though there's something up there that we could have used. I'm just going to do them separately. So let's do the 2 over x plus 1 first. That's writable as 2 over 1 plus x, which is 2 over 1 minus negative x. So equating that to a over 1 minus r, a is 2, r is opposite of x, and so that series is equal to sigma from n equals 0 to infinity of a, which is 2, times r, which is the opposite of x, raised to the nth. And its interval of convergence is found by setting the absolute value of r to be less than 1, and the absolute value of negative 1 is 1, times the absolute value of x is absolute value of x. And so that's from -1 to 1. That's our interval of convergence for that part of the problem. Okay. Now let's do the other one, 1 over x minus 1. Is the same thing as 1 over -1 plus x. And I have two problems, and I actually get to take care of both of them at one time because of the way this is going to set up. That's supposed to be subtraction, and that has to be a positive 1 in the denominator. So if I multiply it by -1 over -1, it actually takes care of both issues, luckily. And so that becomes positive 1 minus x. So if we equate that to a over 1 minus r, then that means that a is -1 and r is x. So that means that the 1 over x minus 1 as a power series is sigma from n equals 0 to infinity of a, which is -1, times r, which is x, to the nth. Okay? So, since our original function was rewritten using partial fractions to be 2 over x plus 1 plus 1 over x minus 1, that's equal to, by substitution, sigma n equals 0 to infinity of 2 times the opposite of x to the nth plus sigma n equals 0 to infinity of the opposite of x to the nth. Oh, and I forgot to do the interval of convergence for the second one, so let's do that. That means that the absolute value of r, which is x, has to be less than 1, which means that x is between -1 and 1. These happen to be the same interval of convergence. Actually, what you would do is, if they didn't agree, you would have to find the intersection of their intervals of convergence. Let's say, for example, we had one of them, and I like to do this on a number line because it makes it really clear. One of them goes from, let's say, -6 to 3. That's one of them. And then the other one has an interval of convergence from -2 to, say, 7. I'm just making this up. Okay, so where they would intersect, the interval of convergence for the sum or difference of those two, things like ours to the left, would be the intersection of those two intervals. So that would be from -2 to 3. So that's if they're not the same, you only can use the interval of convergence's intersection, because it has to converge for both of them, and that only happens where the two intervals overlap. Okay, but anyway, this one has an interval of convergence. I might as well write it. The intersection of -1 to 1 and -1 to 1, of course, is -1 to 1. And let's do a little simplification, if you don't mind. This would be the same thing as two, and then that -x to the nth is a product raised to a power, so I can take each factor and individually raise it to the nth power. And that minus that -1 can come out in front of the sigma, like that, making that x to the nth. Then the difference of those two sigma formulas, since they both go from n equals 0 to infinity, they can be combined. So that's going to be 2 times negative 1 to the nth times x to the nth minus x to the nth. Then we can factor out the x to the nth behind, because that's a common factor. That would leave 2, oops, forgot to write the 2, negative 1 to the nth minus 1 multiplied by the common factor x to the nth. And if we wanted that in expanded form, putting in 0, negative 1 to the 0 is 1, 2 times 1 is 2, 2 minus 1 is positive 1, times x to the 0, which is 1, becomes 1. Then put in 1, negative 1 to the first is negative 1, 2 times negative 1 is negative 2, negative 2 minus 1 is 3, negative 3, excuse me, negative 3 times x to the nth, and x there was x to the first, so minus 3x. Then the next one, put in 2, negative 1 squared is 1, 2 times 1 minus 1 is 1, so positive 1, times x to the 2, so that's x squared. And if you continue, you'll get minus 3x cubed plus x to the fourth minus dot, dot, dot. And as already said, the interval of convergence for this series representation of f of x is from negative 1 to 1. So that function converges to that series for any x value between negative 1 and 1. That's what we're finding when we do that. Okay, we still have a little bit left to go, and I've run out of room, so I'm going to go to the next recording.